Having written down the Lorenz equations, let's now examine some basic properties that emerge from these simple equations. Now, as I've alluded to previously, there's no systematic methods to investigate these systems. Each system presents its own challenges, and one has to invent extemporaneous analyses to try and understand the long-time behavior of these systems. But before doing so, let's try and see what we can learn by just looking at the equations themselves. So let's look at some basic properties of the Lorenz equations. So first point is that they're nonlinear and coupled and also three-dimensional. So therefore we expect complex behavior from these equations of motion. The other simple property that one can see just by inspection is that these equations have a symmetry. If I take x and y and send them to minus x minus y, the solutions are invariant. So there is the symmetry in the equations of motion. But here now comes a much more powerful and important property, which is the notion that these equations of motion are dissipative. Or maybe another way to say this is that they're volume contracting. And so what I mean by this is the following. Let's suppose we prepare many copies of the Lorenz system with a whole range of initial conditions that fill up some volume V in the space XYZ. So we have, say, some volume V, and we have an initial condition which is inside the volume V, and we have a whole set of initial conditions which fill up this volume. And then we let the Lorenz equations run. And an amazing feature of the Lorenz equations is that the size of this volume will necessarily shrink with time and exponentially go to zero as a function of time. So this imposes an incredibly strong constraint on the types of long-time behaviors that can occur, because the long-time dynamics is going to be restricted to sets of not a full three-dimensional system, because the volume of any possible set of initial conditions goes to zero. So let's see how that actually happens. So what I want to do is I want to compute the volume of my set of conditions at a time t plus dt and relate it to what the volume was at some time earlier, volume at time t. And the idea here is very simple, and it's something that anyone who's taken a course in electrostatics will maybe appreciate this or have seen examples like this in the past. But let's imagine that we look at a small area element on the surface of the volume V and ask how much probability flow is there out of the volume in a time dt. To simplify matters here, let me think of this three set of equations. Let me write it in kind of a vector form. So let me write it as vector r, so that's bold-faced r dot, is equal to L, the Lorenz operator, on r. So that just encapsulates these three equations. And the point is that if we now ask how does the volume change over time dt, what I have to do is compute the flow of probability leaving this area element, and there's an outward normal here, let's call that dn. L dot n, so this is like a vector operator here, L dot n dA is the flow of probability outside of this little area element times dt, because we're doing this over a time dt, and we want to integrate over the entire surface that encloses this volume. So we can now turn this into a differential equation. We can write this as v dot now. I just take this to the left-hand side and divide through by t. So this is the area integral, L dot n hat dA. And now I appeal to a basic theorem in vector calculus that we can convert the area integral into a volume integral. So this is the integral over the area that encloses the volume V. This is the same as the volume integral itself of del dot L dV. And now let's compute this quantity del dot L. So this is going to be d by dx of L sub x, which is the x component of the Lorenz operator. So that's going to be d by dx of sigma y minus x plus d by dy, the y component of the Lorenz operator, which is rx minus y minus xz. And finally, plus d by dz of xy minus bz. And so this is easy to evaluate. From the first term, we just get minus sigma. From the second term, we get minus 1. And from the third term, we get minus b, which is clearly less than 0. Finally, we have v dot, which is the volume integral of del dot L. Del dot L is a constant which doesn't depend on the volume, and so the volume integral just gives me the volume back again. And so what I get is minus sigma plus 1 plus b v, or asymptotically v of t goes as e to the minus sigma plus 1 plus b t. All volumes shrink to 0 for any particular volume that defines a set of initial conditions. So what are the implications of this very powerful statement? So the first point is that from this we see that there can be no limit cycles because a limit cycle does not obey volume shrinking. There can also be no unstable fixed points because if I did have an unstable fixed point, then the flow would be outward and there would be volume expansion. What it means is that the fixed points can only be of two types. They can either be stable, which is obviously volume shrinking, or they can be saddle points. For a saddle point, there is flow inward in one direction, there's flow outward in orthogonal directions. So it's not obvious that this is a volume shrinking type of situation. But as we'll see, saddle points do exist in the Lorenz model, but they do exist in a volume shrinking nature, and that's what gives rise to the convergence of trajectories onto things called strange attractors.